big thing in one shot. That gives you a lot of power. Right? So the fact that you can flip everything. All right, let's get going. So I got an email from the campus saying that we may hear some chimes because this is the 150th anniversary of the founding of the university. Okay, so you may hear some chimes between 11 and noon sometime. Okay, so that's my reminder. Chimes, right? You know. So if you hear it, you know, you'll say, ah, wonderful. Okay, let's finish selection before we move on to other things. Am I too loud? I guess so. This one is. Can people in the back hear me? Okay. Okay. All right. So let's recap selection, right? What is selection? I give you an unsorted array and I give you an index and I want to find the jth index j and I want to find the jth ranked element, right? Yeah, and of course you can sort and you can find the jth ranked element easily, right? So that's n log n time. The question is, can you do better than n log n? And we said we can do it in linear time, right? And what is the idea? The idea is, well, let's try quick select, right? Quick select is very simple, right? Quick select is a variation of quick sort, where you take a pivot, pick a number from the array and use it to split the array into two halves, or not halves, two sides. All the numbers less than the pivot and all the numbers bigger than the pivot. You can do that in linear time, right? Pick all the numbers less than the number, put them on one side, pick all the numbers bigger than that. In one scan, you can do pivoting, right? Given any number. So if you are looking for this array and you want to find the fourth ranked element, if you pick 16 as your pivot, you split the array this way, and then you know, because you know the position of 16 in the sorted array, you know its position is 6. So you're looking for the fourth ranked element, so it must be on the left hand side, right? So you recurse only on the left hand side. Yeah. So that's the idea of quick selection. The only catch with quick select is that if you're not careful, your pivot might make the split unbalanced, right? In that case, if you just do quick select recursively, it can lead you to n square times, right? So on the other hand, if somehow magically I am able to pick a good pivot, what's a good pivot? It sort of splits the array roughly into two equal halves, right? Then I've spent linear time and cut down the problem size by a constant factor. And if you look at the recurrence, I mean, so I get n plus n over 2 or n over 4 and so on, and that converges to 2 times n, right? So if I can do that, if I can always find a good pivot, then I will get linear running time, which will be very nice. Okay. The question is, how am I going to find a good pivot, right? And the idea which people came up with, which is not trivial, is that okay, I want to find something interesting. So what would we do? We took the array. And we said, okay, we'll group the elements of the array into groups of 5, right? Okay. And then within each group, we'll find the median of that 5 elements. That's easy, right? It can take constant time. So we spent still linear time to find, after grouping, we find the median of these 5 elements, the median of these 5 elements, median of these 5 elements. Here the example is showing 3. And then we take those medians, how many of them are there? N over 5, right? Because there are n over 5 groups roughly, right? And we find n over 5 numbers now. And then the claim, mathematical claim, which is interesting, is that if I take the median of those n over 5 elements, then that's an approximately good median for the entire array. Okay, that's important to remember, right? We are only computing the median of this n over 5 elements, and then that is a number, right? A number in the array. If you then use it in pick select, it will give me a good balance. Okay. So what have I achieved by this? Because computing the median seems already expensive, right? Because that's another selection problem. Except that, I'm only trying to solve it on an n over 5 sized array. Okay. So it's like, oh, okay, look, to find a good median, I'm calling selection again, but on a smaller problem. Will this eventually lead me to anything interesting, or will it blow up, right? So that's something that we need to work out. And now for that, we need to understand what is the precise mathematical statement I can say that about how good is the median of medians going to be for the entire array. And this is a statement we can make, that if you look at the median of those n over 5 medians, then what does it mean that it's approximately good median for the entire array? We can claim this statement, that if you use that as the pivot, then both sides won't be more than 7n over 10. Okay, I'm not getting exactly a half split, right? That would be great, right? But I'm not going to get a half split, but I'm going to get an approximately good split. Okay, what does that mean? That means I'm guaranteeing to you that if I use it as a pivot, I'll get two halves, right? Two left side and right side. Okay, the size of both left side and the right side is between 3n over 10 and 7n over 10, right? So then neither side is too small or too big. Yeah, they're roughly half. They're not exactly half, but roughly half. Okay, okay. So that is the mathematical statement. And so what is the algorithm using that? The algorithm, remember, we're trying to find the jth ranked element in array A with n elements. You first form this n over 5 lists like we did. Now, in each of those lists of 5 elements, you find the median bi, right? So b1, b2, bn over 5. Now, okay, so now let me do this one, right? So you find this b1, b2, bn over 5. You create a new array b, and now you want to find the median of those n over 5 elements, right? Okay, how are we going to find it? We don't have any way of finding a median, right? But it's a selection problem again, right? Finding the median is a selection problem, so we recurse. Okay, so we recurse on a smaller array. So we're finding remember it's the same select, but on a new array B of only n over 5 elements. But we want to find the median, right? What is the median? It's a half ranked element, right? So with the n over 5 elements, we are trying to find an element of rank n over 10, right? Don't worry about the floors and ceilings. That's kind of minor annoyance, okay? Okay, so we're finding the middle element in this array B, and then we are going to use it as a pivot, right? So then what are we going to do? We are going to use that as a good pivot to partition A into A less and A greater, like we do always with quick select. And then we have to, again, we still are not done, right? We found to find the jth ranked element, right? So where is it? Well, after you partition, you have to either recurse on the left or the right on the natural way, right? Depending on the rank of J and the rank of the pivot. Yeah? Make sense? Yeah? Okay, now what is the running time of this algorithm assuming the mathematical statement, right? Okay, well, it's a recursive algorithm. We just write a recurrence, right? So we start with an array of size n, yeah? Okay, so what do we do in this work other than recursion? If you don't worry about recursion, what is the total amount of work we do? I claim it is constant times n. Why? Because what are we doing? We are creating this array B, we are computing the medians of 5 elements, n over 5 times. All that is only going to take some constant times n, right? The work outside of recursion is only constant times n. Is that okay? Yeah? So my claim is that the recurrence is T of n is, this is the work I do outside of recursion. But what about recursion? I recurse on, to find this I have to recurse, right? I recurse on an array of size n over 5. Right? So that is this recursion. I have to recurse again because once I split, I have to recurse again, right? Which side I will split recursion? I don't know, right? I may split, go on the left side or I may go on the right side. Okay? Do I know its size? I don't know the exact size of the left side or the right side, right? So it is going to be something, right? That's why I put less than equal to. And I'm saying, I don't know exactly, so I'll upper bound it. Okay? How am I going to upper bound? I say, okay, I don't know which of these is smaller, but take the greater of those two things, right? Okay, it's a small technicality that is really a upper bound. But from the lemma, we know that the bigger side cannot be more than 7n over 10, right? Yeah, whatever is the bigger side cannot be more than 7n over 10. So my recurrence is t of n is less than t of n over 5 plus t of 7n over 10, don't worry about 6, plus O of n, some c times n, right? And what is t of n for small n less than 10 is some constant, big constant, right? Okay, now what is the solution to this recurrence, right? I claim it is O of n, okay? Now, I mean, maybe it's not intuitively obvious, but I want us to get to the point where we say, aha, this is O of n. Why? Because you can draw the recurrence tree, right? Okay, so let's draw the recurrence tree, right? But then we get a better sense of, I mean, what exactly is the intuition. The guys who designed this algorithm were not were using the intuition for the recurrences to design this algorithm, right? So let's see what does it mean. That can we get to their their state of mind, right? What did I do? Okay, so t of n is less than t of n over 5 plus t of 7n over 10 plus some, let's for some c times n, where c is some constant, and t of 1 is okay. So let's draw the, I mean, whenever we have recursion, we draw, right? Okay, 7n over 10, right? Okay, and then, you know, what happens here? N over 25. Well, now it's getting a little ugly, right? 7n over 50 and 7n over 50 and 49n over 100. Okay, all right, messy. Okay, Cn, right? What about the work here? Cn over 5. Okay, can I ignore the C? Yeah, C is 1 for simplicity, but otherwise the C will. Okay, I'll ignore the C for notational ease. So it is 7n over 10. Okay, now we have to do our obvious thing. We have to add up all the work, right? It looks a little messy, so let's try to do level by level, right? One thing to try to do is level by level, just to understand it. So what is the work at this level? N, right? What about the next level? It's n over 5 plus 7n over 10, right? What is it? 9n over 10. Okay, what is the next level? Okay, we will do some algebra. Okay, can somebody guess? Okay. All right. Oh, sorry, 100. Yeah. Thank you. Okay. Sorry, is it 72 or what I wrote right? Yeah. Okay. I did it without thinking because I know it's right. Okay. No, that's not the reason. Okay. Okay. I know why it is true, because it is, you know, once you get used to it, you don't think it too, right? You know, why is that? Okay. The fact that there are two problems is not the interesting thing, right? First, remember, this is linear, right? It's n, right? So what is the sum of the problem sizes here? 9n over 10, right? So because it's linear, it is 9n over 10, that's what we got, right? Okay, so but by the same logic, because the recurrence is the same, this will be 9 over 10 times this size, and this will be 9 over 10 times this size, right? So this size, so basically we'll get 9 over 10 times 9n over 10, okay? All right, the fact that there's two problems is not the most interesting thing, okay? So, okay, is it going down or up? Okay, so it is as if, it's the same thing as if I had one problem and it went down to 9n over 10. Okay, it's the fact that it's two problems is not so interesting. It's the same thing as as far as the sum of the work is concerned. I've taken a problem of size n, I've made it into 9n over 10. Okay, and I spent linear work. So I've reduced the problem by a constant factor, no? Okay, So that's it. So we should get linear time, all right? Okay. Again, right? So if you add this up, you can do the algebra, right? Algebra is not going to cheat you. You can do algebra, right? And you'll realize that it is same as n, 9n over 10, 81, so 9 over 10 square times n, 9 over 10 cube times n. So that converges to 1 over n, right? Okay. So, but how do we intuitively think about it, right? Intuitively what we think about is the fact that we are breaking up into two problems is not such a big deal as long as the sum of the problem sizes is a constant factor less than the n, right? So the fact that we have two problems is not the interesting thing. It is the sum of these problems is n over 5 plus 7n over 10, that is 9n over 10. So effectively, even though we are recursing twice, we have made sure that the total sum of the problem sizes that we are working with is a constant factor less than n. Okay? So that gives you again convergence. Okay? Now, the people who designed these algorithms knew this before they designed the algorithm. Okay? But that's because, once you know analysis, you look for what will work rather than the other way around, right? So when I describe an algorithm, I can describe the algorithm and give the analysis to you, right? But what about the designer? The designer here, the designers were very famous people. They knew this math, okay? This math is very elementary at some level, right? They knew the recurrences. So they're saying they designed the algorithm precisely because they said, aha, if I can take the problem of size n and somehow cut down into any number of problems so that the total size is small, then I'll be done, right? So analysis can inform design too, not just analysis comes after the design, right? Knowing the math will help you design algorithms. Okay, all right, so you have to kind of get a feel for this. And now I have to prove to you the mathematical lemma, right? Why is the median of the medians a good median for the entire thing? That's actually very simple once you see it, right? So let's give you a pictorial proof, the formal math you can do it like. So what did we do, right? We took these n numbers and assume n is divisible by 5 to make our life a little easier. So we put them into what? Buckets of size 5, right? And what did we do? We basically, once we put them into buckets, we found the median of those 5 buckets, right? So what does it mean? So we found yellow guy is the median of those 5 numbers. So when we find the median, what we'll do is that we'll take the 2 numbers which are smaller and put them here, and 2 numbers which are bigger and put them here. Okay? So I shuffle that group, okay, and put them above. And so for every column, I do that. Okay? Does that make sense? Okay. So now what happens? What did we do? We took these n over 5 guys, right, and found the median of them. Okay? Right? That's what we did, right? Okay. So this guy is, so whenever we find the median, what does it mean? This is just for a thought experiment. I'm not doing any work actually, right? This is just a mathematical statement, right? So the median is somewhere in here, okay? So I want to claim that all these numbers must be less than the median. Okay? All the guys in this top left corner must be less than this. Why? Okay, well, because this guy is the blue guy is the median, all these numbers are less than that, right? Okay, and in each column, all these 3 numbers are less than equal to this number, right? And so these 3 should be less than the blue guy, right? Okay, so all these top corner numbers we know are less than the blue guy, which is the nice, right? But the same argument, all these bottom corner guys are bigger than the blue guy. Okay. So what have I convinced you? Right? How many numbers are here? There are n over 5 groups, right? So 3 times n over 5, right? Yeah. And no, not 3 times n over 5. Sorry. There are n over 5 groups, but there are only n over 10 guys here, right? This is n over 10, right? Okay, the total number of groups is n over 5, right? But how many are there in this top corner? Only n over 5, right? Because the median is in the middle of n over 5. So this is the n over 10th guy in the n over 5 groups. So the number of guys here is n over 10 times 3. Yeah, right. So 3n over 10 are in this corner. So 3n over 10 numbers are less than the blue guy. 3n over 10 numbers are bigger than the blue guy. Do I know anything about the relationship between this guy and the blue guy? I don't know, right, what the relationship is, right? I have no idea. I have no information. Okay. So what we can argue is that there are 3n over 10 numbers less than the blue guy, 3n over 10 numbers bigger than the blue guy. Okay. So that's why the median of the medians is somewhere in between, right? Okay. But we don't know exactly where it is. So it could be that, there are 7n over 10 numbers bigger than that guy, right? Right. So that's the worst case, is that the one of the arrays after we do the pivoting is 7n over 10. Okay. All right. Does that make sense roughly? Okay. If it is not, go back and think. Okay. Yeah. So in each column, these three numbers are less than this blue guy, and there are n over 10 columns in that. N over 10 columns, right? N over 5 is the total number of columns, and only half you can say, right? Because the blue guy is a median. Okay. Right? Okay. So mathematical statement has nothing to do with the algorithm, right? We are just doing this argument. Yeah. The minus 6 is because what if n over 5 is, n is not divisible by 5, and maybe in this column only 2 guys are smaller than this. So don't worry, it's all noise. Okay, that is just to be precise. Okay. Because no, we see. So this is a good question. What if they're all the same? He's saying, right? So there is a simple trick to make life easy. You pretend they're not the same. Okay. Okay. All right. What does it mean, right? How can you pretend that they're not the same, right? There is a trick that we'll come to later on too, but let me tell it to you right now. How do you formally pretend that they're not the same? Okay. Okay. Can you formally pretend that two numbers? So what does it mean? That if two numbers are in an array and they're actually the same value, you want to break ties in some reasonable way. How will you break ties? Sorry? Yeah, so basically you sort of create an artificial new index, right? Where you say, okay, you make the number, comma, its index in the original array. So you replace all numbers by a number plus its index in the original array. Now when they're equal, you say that if they are equal in the value, but the one which comes before the other one in the original array is smaller somehow, right? So you can pretend that no two numbers are the same formally in this way, right? So you can always tie break like that. Not always, I mean, for most applications you can tie break, so it's just a mathematical argument, right? Okay? So you can pretend that, or you can add noise or something like that. Okay? Okay, that's the selection algorithm, right? So now, I mean, you shouldn't necessarily, the idea of selection here is that once you know that you can do selection in linear time, now you have a black box to do selection, okay? Just like you do sorting in n log n time, you don't think, right? Maybe you remember merge sort because it is easy algorithm, you can recreate it if you want. But selection is a little tricky, You may not remember this algorithm very well, right? All the details are a little tricky here, right? It's not a straightforward algorithm. So you don't need to worry about it for the most part, because now it's a black box. Now you have one more thing that you have in your arsenal, right? If I only need to do selection, I can do better than sorting. Now you don't need to remember the details of how, who, etc. Right? That's a very important skill in algorithm design. Outsourcing, right? Right? You don't want to always remember the precise details of the algorithm itself. All you need to know is that it can be done. That's not called plagiarism. That is called outsourcing is okay. It depends on the rules of the game, right? So remember, our rules are that you can cite, right? That's precisely because we gave up on trying to catch people doing plagiarism. So we said, okay, at your own risk. Okay. All right. So that is selection. It's the first non-trivial algorithm you probably have seen, which is based on recursion, and okay, all right. Now we are going to go towards dynamic programming. Okay, so dynamic programming is a tough technique to learn. Okay, I'm going to put it out upfront because it is a little tough. Okay, it requires you to understand recursion well. So we're going to go slow. Okay, but it's a very powerful technique, right? Why is it powerful technique? Well, it lets you solve problems which on the face of it don't look like they can be solved efficiently. Okay, there are many practical applications, and even if you don't care about anything else, definitely if you go to a Google interview, they'll ask you a question on dynamic programming, right? So be pragmatic, even if you don't care about the theory, right? I had an interesting experience that I was at the Champagne airport. This was last time I taught 374. So this student came he was coming out from the flight, and he came running to me because he saw me and said, I just came from a Facebook interview, and here is a question they asked and I couldn't solve it. And I said, but this is exactly what I covered in lecture, right? And he said, oh man, okay, all right. So don't have that experience, okay? So try to remember, right? Let's see. So dynamic programming is one variant of recursion, right? So we'll get to that. But to get to dynamic programming, right, we have to get to know recursion better, right? So you have to get more comfortable with recursion, understanding what is the structure of the problems that the recursion generates, right? What is their meaning, so we need to get a little bit more comfortable. So to do that, we'll just start with some just recursion without worrying about the the memoization and stuff. So take this problem, right? What's called the independent set problem, right? We saw this already, right? What is this problem? I give a graph, and I want to know what is an independent set in this graph, a set of vertices such that there are no edges between them, right? Yeah, so D is an independent set in this graph, right? A, C are also independent set because A and C don't have any edges between them. B, E, F is also independent. Yeah? Okay, good, easy enough. The problem I'm trying to solve is find the independent set of largest size in this graph. Okay, does that make sense? Okay, good. How will we solve it? You can also put weights on it, right? You can put, say, this guy has weight 50, this guy has weight 100, that guy has 0, and so on, right? And then you want to find the maximum weight in it. So it's known to be a very hard problem. Okay, we'll see why it is a hard problem. It's called an NP-complete problem. Okay. So we don't know how to solve it, but let's say, what would you do if I gave you this problem, right? So what's the brute force solution for this problem, right? You can try all subsets of vertices, no? You say, take the subset. Is it an independent set? Okay, if it is, then we say what is the size of it, and you can just loop, right? Okay, how long will that algorithm take? So if the graph has n vertices, how long will it take? Sorry? Yeah, what exponentially? Precisely, let's be more precise. 2 to the, okay, but what else? It needs bit more work, no? Just 2 to the n is sufficient? I mean, just to be precise, right? Is 2 to the n, for each time we have to do some work, no, to check that it's an independent set, right? So how long will that take? You have to check some m time or m plus n time, right? So it is 2 to the n times m plus n, right? Yeah, you can't just 2 to the n, right? We know it's exponential, but exponential times another big number is still bigger, right? Okay, so it is 2 to the n times some polynomial. It's still exponential, right? Okay, so clearly, suppose you have a small graph, right? Maybe you can try this brute force. But even in this, it is helpful to maybe not do as much work as the brute force is saying, right? Brute force, the disadvantage of brute force is what? That you are going to be stuck with the 2 to the n running time even if I give you an empty graph, right? If I give you an empty graph, your brute force algorithm will take 2 to the n time, even though you should just simply say immediately that it is n, right? So in a sense, can we make it a slightly better algorithm by being a little bit more careful by recursing, right? Can you come up with a recursive algorithm instead of trying brute force? Okay. How would you express this, even just this enumeration, how would you express enumeration as recursion? Can you solve this problem recursively? Can you make it, it doesn't matter what the running time is. The idea here is to think recursively about solving problems. So what does it mean to recursively solve this problem? I want to take a graph and I want to make it smaller somehow, right? Okay. How can we simplify the graph a little bit? Right? We are trying enumeration, but I'm just thinking, can we make enumeration a little bit less dumb, right? Or think recursively. So I want you to come up with a recursive algorithm. I insist I want a recursive algorithm, right? Just because you want to think recursive. Yeah? Yeah, graph problem, yeah. So I give a graph. How will you simplify it to make it and then do something with it?
So I'm going to start with B. You can say, C and A and C is not independent. And once you check that B and E is independent, then you can check to see what E is independent.
No, but I want so is that recursive? I mean, so.
Once you, I would say it is recursive because you're checking what E is independent of. Once you find out that E and E are moving to something else.
Yeah, but what did you simplify the graph? Did you make the graph a little smaller graph, or are you just working with vertices?
You don't check the previous one, you just check. You don't check A. Already check A.
Okay, let's think a little bit more high level. Okay, one hint. Let me think. See if you can help. Suppose I want to remove one vertex. Can I remove one vertex out of the graph and say, suppose I remove any vertex f, for example. What happens? The graph becomes smaller, no? Okay, now I can find it recursively a best solution for that graph. Why would that not be the best solution for my original graph? Yeah? Because f could be in the best solution, right? Okay, so there are only two possibilities, right? If I remove a particular vertex f, for example, either the optimum solution is in the graph where f is removed, yeah, or it should include f, right? Okay, but if I knew that it should include f, what can I do to simplify the graph? Okay, but does it simplify the graph? How should I make sure that if I want to include f, okay, maybe let me ask a question. What is the best solution in this graph where I insist that f should be in the solution? Among all solutions, find the one which has f in it. Does it make the resulting problem smaller? Yeah? Yeah, good, right? If I want to include f, what should I do? I should set aside f, right? Because I want to include. And then kill all the vertices which are adjacent to f, because they cannot be. If I want to have f in my solution, I should remove everything, right? Okay, so now we have a recursion, right? Why? Pick a vertex f, okay. Either I throw f out, I get a graph without f, I find the best solution in that graph, recursively, right? Why? Because I reduce the graph size by what? 1. Okay, but it's still smaller, no? It's still smaller, right? So that gives me one solution, but that may not be the best solution. So what should I compare it with? I include f, that means I say I want f in it, and I remove all the neighbors of f and recurse on the graph where f and its neighbors are removed, and I have to add 1 to it, right? Because okay. So what am I trying? I'm expressing my solution as the best of not having f and having f, right? That's also enumeration, right? I'm trying all possible solutions which have that particular vertex in them, and all possible solutions where that particular vertex is not in them. Clearly, I'm basically essentially doing all possible solutions, right? But in both cases, I'm going to make the graph a little simpler, no? Okay, so that is one way of doing it. I'm not saying that's the only way. So what is the graph, right? So here is the recursive algorithm. We order the vertices arbitrarily, and notation wise for a vertex u, let n of u be the neighbors of that vertex, right? Just notationally. So here is that we can break up the solution space into two sets, right? Those solutions which contain this vertex v1 and those solutions which don't contain vertex v1, right? And so we find both, right? So if G1 is a graph where we remove the vertex v1 and G2 is a graph where we remove vertex v1 and all the neighbors of v1, then my claim is the maximum independent set value in the graph G is the maximum of MIS of G1 and MIS of G2 plus the weight of v1. Yeah, does that make sense? Okay, simple enough. Okay. So the idea being that both G1 and G2 are smaller graphs than G, so I am really recursing. Yeah, okay, so okay, that's it, that's the algorithm, right? If G is empty, then output 0. Otherwise, you compute A, which is the recursive MIS of G minus V1, you compute recursive MIS of G minus V1 minus N of V1, V1, and you add the weight, and then you take the best of the two, right? Yeah? Question on that? Okay, yeah? A maximum independent set. Yeah? Yeah? Just to not write everything down. Yeah? Okay, so what is the advantage of this graph? Even heuristically, this is what people do, right? What is called, it's called branch and bound or something, right? So why is the advantage of this graph over the blind enumeration? So here is the thing, right? Suppose you start with this graph. Which vertex should I choose? Okay, what did I choose? I think I chose this vertex, right? I chose a high degree vertex, right? I could choose any vertex to do this, right? It wasn't particularly. So I generate two problems of what? Smaller size, right? Okay, so I get two problems, and then once I get the solution from this, I have to compare and take the better of the two, right? And how will I solve this? It will generate two problems, right? Okay. The nice thing is that at some point, if there are no edges in the graph, I know the answer, no? Yeah. So I don't have to recur simply blindly, right? I could do something a little heuristically clever, saying, aha, see, look, this graph is very simple, I know how to solve it. Or this graph is very simple, I know how to solve it, right? See, this is a much faster algorithm than just trying all possible 2 to the n irrespective of the graph, right? Yeah? Okay? But that's how it comes from. This is just called, just branch and bound. In the worst case, it can take 2 to the n time. Okay? But in many practical situations, it will do faster. Right? That's not the reason why we care about this, because we want to think recursively for every problem for a little while. Okay? Yeah. So this recursion depends on the order I'm picking this vertices in, right? No, it doesn't change the solution. Why is that? It doesn't change, right? Because I'm comparing the best of these two, no? Why would it change? Because, that's important observation, that irrespective of the vertex I pick, this recursion is correct, no? The max of the solution here and the max of the solution of where I include the vertex and find the maximum of this, that is correct. Why is that? I'm looking at the solutions, possible solutions, and every solution is either here, you partition all the independent sets into two sets, those that contain this particular vertex and those that don't contain this particular. So this one will make sure that it finds the best among all the ones that which don't contain that vertex, right? And this one will find the ones which contain that vertex, right? So for every vertex that's true. So I am allowed to branch any way I want on any vertex. Okay? So you can pick the vertex cleverly if you want to make it faster, but you don't have to pick it cleverly. The recursion is correct whatever vertex you pick. See, here I chose this vertex because it has high degree to make it a little faster, right? That's just a heuristic thing, right? Okay. Okay. So that's important. Okay. The running time will in the worst case be 2 to the n, right? So this is called, how will you solve this? In practice, what will happen is that you recurse, and then can you improve it even better? Okay. So what you can do is that this is called backtracking search, because what will happen is that suppose you've already found a good solution on this side, okay, and when you're doing the recursion on this side, if you get to a place where you know that there's no way I can beat this solution, you can even stop the search. Okay, so that's actually another heuristic improvement. I mean, I'm saying all this because it's actually used, right? But the important thing is recursion. Okay, so let's do one more problem, right, to get the hang of recursion. Okay, we'll play with the sequences for the next 2 lectures. A lot of sequence problems, because they all are amenable to dynamic programming for a lot of reasons. So what is a sequence? Just an ordered list of numbers or objects, right? A1, A2, An. What is the length of the sequence? How many are there in the sequence? And what is a subsequence? We already know what a subsequence is. Yeah? What is a subsequence? There's a difference between substring and subsequence, no? Subsequence, I'm allowed to skip things, right? Okay, so I1, I2, Ik, they're ordered, is a subsequence obtained by just dropping everything else and keeping those parts of the sequence. So we'll say sequence is increasing if, just a sequence of numbers, if all the numbers are increasing in they're sorted in the right order, right? The sequence is increasing, right? If all the numbers are going up, right? It's decreasing if they're all going down. Yeah? So far so good? Okay. So here is an interesting problem. I give you a sequence, right? 6, 3, 5, 2, 7, 8, 1, 9. Okay, okay, you see, it's just a sequence, right? Okay, so everybody this is just definitions. I want to find, this is an interesting optimization problem, right? I give you a sequence and I want to find the longest increasing subsequence. Okay, what does that mean? Okay, so 6, 3, 5, 2, 7, 8, 1, right? I want to find a subsequence that's increasing. What is the subsequence that is increasing here? 3, 5 is increasing, right? Okay, but what is the length? 2. Okay, but 3, 5, 7, 8 is also increasing, right? That is what is its length? 4, right? So I want maybe 3, 5, 7, 8 is clearly better. What is the longest increasing subsequence of this? Okay, it turns out to be 3, 5, 7, 8, right? Maybe it's something else too, but okay. Okay, that's what I want to solve. I give you a sequence, you need to give me the longest increasing subsequence. How do you solve it? Okay. Is it? Okay. So this is a problem for which it is not immediately clear that whether it can be solved even in polynomial time. Okay. Okay. Unlike, for example, sorting or selection that we have seen earlier, where the only thing that divide and conquer helped us with is what? Make the running time faster than what we already kind of knew, right? If I told you to sort, you will come up with an n square time algorithm, right? Merge sort helps you get n log n, which is much faster, better, right? For sure. But the fact that it is solvable in polynomial time is not the hard part, right? In sorting or selection, that is very easy. Maybe it's not the most efficient algorithm you can design, but in this kind of problem, it is not obvious at all that this can be solved in polynomial time. Okay? And it is solvable in polynomial time using dynamic programming, but we'll get there, right? But the point is, how do we solve this recursively? Can you think of a recursive algorithm for this? Sorry, O of n square. How? No, but it's a subsequence, it's not a... Yeah. Okay, how will you check the longest increasing subsequence from starting with 6? Okay, but I don't, and that's precisely what I'm trying to solve, no? So are you saying, are you giving me a recursive algorithm, or are you saying that it exists? I'm saying, you may know that this problem can be solved, but I'm saying, you know, I'm not seeing what you mean by your algorithm. No, I mean, it's not the same as the longest increasing contiguous subsequence. No, this is not contiguous, right? 3, 5, 7, 8 can jump, right? Yeah. Yeah. How? Unless you give me a recursion, how will I check? Mm-hmm. Yeah. Yeah. No, but that you know that doesn't. I mean, I don't see what your algorithm is because. Okay, where am I? Okay, in the interest of time, probably he has something in mind which is not clear to me. But can you think of an algorithm for this which is recursive? See, the important thing is I want you to give me an algorithm which is correct without you giving me complicated details, right? That's the nice thing about recursion, right? You know, it enables you to quickly see something is correct. Yeah. Yeah, so he's saying, you know, let's try recursion by saying, you know, there are two cases for the first number, right? Yeah, I mean, the longest increasing subsequence either includes the first number or it doesn't increase the first number. So we can try to recurse like that, right? If it doesn't include the first number, we can just recurse on the remaining array, right? Okay, we read. But if it includes it, what happens? Yeah. Sorry? Oh, he wants to start from the other side. Doesn't matter. Okay. Okay. Oh, so okay. We want increasing subsequence. So okay, maybe look at the one, right? We will go from the other end, right? Maybe that I prefer that too. So just for my notational thing, right? So one case is that I don't want to include the last guy in my sequence. So then I can drop it and recurse on a smaller sequence, right? So, but if you want to include that guy, what should I do? I want to include one in my longest increasing subsequence. So that means I won't end up there, right? So how can I find the longest increasing subsequence which ends up with that last guy? So I have to remove everything that is bigger than 1, right? Because they cannot be in any longest increasing subsequence that ends in 1, right? Okay? So in both cases, I make it smaller, right? Because I know I want to include 1, yeah? If I want to include 1, I get rid of everything which is bigger than 1, and I get rid of 1 too, because then why? Because I can recurse on the sequence with numbers less than 1, and the longest increasing subsequence on that, I can tack on 1 on it. Yeah? Is that okay? Yeah? Okay? So that's the reason thing, yeah? Yeah.
The way the problem is set up,
Mm-hmm.
if you're on the rightmost number,
Yeah.
that has to be the biggest number.
No. I mean, in the eventual solution, yes. No, not necessarily. Why?
Because so.
I mean, here is another example. No, the problem is not so obvious, no? What if my sequence is 8, 5, 7, 7, 1, 5, 7. It doesn't include 8. Yes, so I'm not. What is your claim then? Oh, that could be true. Okay. What if it is bigger? No, not necessarily. Not necessarily. Right. Okay, I could have this. No. 5, 6, 7, 8, 1, 2. Do I always include 2?
So basically, it's saying, okay, it's 2 greater than 1, you
Yeah, you could do that, but it is not clear that, I mean, you can eliminate one, you're saying. Yeah. Okay, that's another way of recursing, right? You could do that too, right? So my claim is, okay, you know, you can do the recursion, right? You know, here is what, I mean, let's stick with the simpler recursion, right? Which is either we include the last guy, or we don't include the last guy, in which case what do we recurse on? The first n minus 1 numbers in the sequence, right? Okay. But if you include the last guy, it is a little clunky, right? Why is it a little clunky? Because we have to eliminate all the numbers bigger than that, right? And we get what? Something which is a sub-array of the original array, right? But that looks a little bit crazy, right? You know, I mean, it is fine, right? It's okay. So you can do that recursion. That's a fairly simple recursion, okay? But I'm going to give you another recursion because it helps us in some nice way, okay? Okay, so ideally we would like to come up with a clean recursion so that we can see the structure, right? So here is another way of doing it. I'm not saying this is the only way to do it. Okay, so if we could somehow do the following, right? When we want to include the last guy in the sequence, what did we really want to do, right? We wanted to eliminate all the numbers which were bigger than that and create a sub-array of that, right? So that's a little bit hard to do, right? We have to throw out everything and then create a sub-array and stuff. Can we do it in a cleaner way, right? How can we do it in a cleaner way? So here is one way to make the problem a little bit richer, okay? Which makes the recursion cleaner, okay? So what is a new problem? It is just a small twist which looks superficially no different. So I'm going to look at the new problem as I give you a sequence and also one more number x, okay? So my goal is to find the longest increasing subsequence in the array A such that no number in that sequence is bigger than x. Okay? It seems like a superficial change, you know? Does it make sense what I did? Yeah? It's the same problem. I added one more parameter which looks like a silly thing, right? Okay? Why could you not simply eliminate all the numbers bigger than x and then solve the old problem? Right? You could say that. Does it make sense, the new problem? The new problem has two inputs, an array A and a number x. Yeah? What do I want? I want the longest increasing subsequence in the array A, but I insist that all the numbers in that sequence should be less than x. Okay? Okay, my claim is there's a very clean recursion for this. Why is that? Yeah, it's clean. I'll tell you why. Okay. If n equal to 0, then return, yeah, 0, right? Because if the array is no, right? Okay. Okay, one case is what? I don't include the last number, right? The same thing, right? Okay, then what do I get? I recurse on the first n minus 1 elements and the same x, right? Okay. Now in the second case, there's something nice happens. In the second case, I want to include the number, right? Can I include it if it's bigger than x? I can't, right? Because my definition is that I want only sequences who all the numbers are less than x. Okay? But suppose the last number is less than x and I want to include it, what should I recurse on? Sorry? I recurse on okay, but now I don't want to throw out numbers. I can replace x with what? The last number, yeah? Okay, is that okay? Okay, so in the second case, let's understand it. I'm replacing what? I'm including the last guy, right? I can only do it if it is less than x, right? But what is the nice thing is that because I'm including that number, now the new problem I want to solve is all the longest increasing subsequence in 1 to n minus 1, but with numbers less than what I included now, right? So I can recurse on that with a of n. Okay, is that clear? Yeah. Okay. So what is nice about this is that I just replace one number in the recursion. All the problems I am generating look very clean. Okay. What does a problem in this recursion look like? Okay. So let's see an example. Okay. So I want to find the longest increasing subsequence in this thing, right? So what will I do? I have 6, 3, 5, 2, 7, 8, 1, and I'm going to start with infinity, right? Because I don't have any limit. Okay. So what are the two problems I do get if I recurse on this? One is 6, 3, 5, 2, 7, 8, infinity, right? That is, I don't want to include 1 in my solution, right? And the other case is what? 6, 3, 5, 2, 7, 8, with what number should I recurse on? 1, okay? Yeah? Okay? So now you may say, that's a little dumb, right? Maybe I should actually simplify it. Okay, we'll see the merit of it next time. But what about this guy? So then if you don't include 8, we just recurse on this and infinity. If you want to include 8, we recurse on this with 8 in it, right? Okay. So now we can say, is there some so each recursive problem has a very nice structure now. How does it look like? What's happening to these arrays here? They're getting smaller, but they always stay a prefix of the original array. Okay? How many prefixes are there? Only n prefixes, right? So the first parameter in this recursion is always a prefix of the array, right? So there are not that many prefixes, no? And that will be important. What is the second parameter? What are the values it can take? What are all the values the second parameter can take? We started with infinity, but as we go down, the second parameter can change, right? What all values can that second parameter take? Only one of the numbers of the arrays, right? So the second parameter has how many different values? Only infinity, 1, and n values. So there are only n plus 1 values that we'll ever encounter in this recursion for the second parameter, right? In the first parameter, how many different things can we encounter? There are only n parameters that we can encounter, okay? And this structure will be very important when we do this memoization, okay? So that's just, a cleaner recursion, and we'll see why that is useful, okay? Now let me introduce the nice idea that is important in dynamic programming by doing the recursion for Fibonacci numbers. Everybody has heard of Fibonacci numbers? Yeah? It is defined by the simple recurrence, right? Fibonacci numbers are defined with the recurrence. F of n is f of n minus 1 plus f of n minus 2. And f of 0 is 0, f of 1 is 1, right? And why is it interesting? It's only because they have been found to have many applications in both, mathematics and nature. There is not simply because there is some reason why this recurrence keeps coming up. And a lot is known about it. So this recurrence has a solution, closed form solution, okay? And what is the closed form solution? It is f of n is phi to the n minus 1 minus phi to the n divided by square root phi, where phi is the golden ratio. It's a bit bizarre, right? Because you know that all these values should be numbers, integers, but the closed form has irrational numbers, right? You see, for every n, this number is actually an integer, even though it has irrational numbers sitting in it. Yeah? That's kind of interesting, right? No, not interesting? Okay. Okay, all right. That is interesting, I think. Okay. So my goal is to compute the nth Fibonacci number. Okay, I have to write a program. What should you do? Compute the nth Fibonacci number. If I ask you what is the nth Fibonacci number, you can use the formula, right? What is the problem with this formula? Sorry? So how will you, okay, if I actually ask you to compute, fib of 10, what are you going to do to me, right? Okay, so write a code or give me Fibonacci of 20, right? You can look up a list somewhere, right? But thing is, you can use a formula too, right? But if you use a formula, the problem is what? There are irrational numbers here, you have to worry about precision, floating point, right? Right? But the recurrence is so simple, no? So why can't I code up the recurrence, right? I know how to solve it, so I'll say, okay, here is a code for Fibonacci of n, right? Okay, If n equal to 0, return 0, and n equal to 1, return 1, otherwise return this, right? We know how to do recursion, no? Okay, what happens if I implement this? It takes a long time. Why? Okay, so he's way ahead of the game, right? Okay, how long is it going to take? Forever. That's right. Okay, why is that? Can you understand it? Is not as a fact. Yeah. Exactly. So I mean, in the sense that we are blind. We just write a recurrence for the running time, right? Okay, what does the recurrence look like for computing this thing, right? How long will it take? T of n is, if the running time of this algorithm is T of n, what is the running time of this algorithm? T of n is T of n minus 1 plus T of n minus 2 plus, I add one addition, no? Yeah? Okay, so that's it, right? So how does it look like, this recurrence? It has something to do with Fibonacci numbers, no? It looks like Fibonacci numbers. Yeah? Okay, what is the solution to this? You should kind of guess that it looks like the Fibonacci recurrence, no? Okay? And you say, okay, but we know the answer to the Fibonacci recurrence. It is roughly phi to the n. Yeah? So the running time of this algorithm also will be phi to the n. That's why it takes a long time. Its running time is roughly phi to the n, which is 1 plus some constant, right, to the n. So it is taking exponential in n, and we don't have to think because we can just write down the recurrence and solve it. Okay? Okay, but why is it taking so long? It seems like a little dumb. So let's see what it does, right? And instead of doing this, you can also do this simple algorithm, no? Why did we write a recurrence? I can solve this Fibonacci number in a much better way. Here is the algorithm to solve the Fibonacci number. Do you agree that this will solve the Fibonacci number? Okay, what do? I compute Fibonacci of 2, 3, 4, 5, 6, 7, 8, all the way till I reach n, right? Okay, I agreed. How long will this take? N time, right? Okay, so why is my recursion taking exponential time and this simple algorithm taking n time? What is my recursion doing? So let's look to see what the recursion is doing, no? What is my recursion doing? It is, we can look at what the recursion is doing, right? If I give it Fibonacci of 10, what is it doing? It's 8 and 9, right? What does 8 do? Okay. Now you see the problem? Yeah? So the same problem is being generated again and again and again, right? That's why the recursion is taking exponential time while the iterative algorithm is taking only small amount of time, right? So clearly we shouldn't do this recursion, right? We should avoid doing this recursion. How? Okay. We don't want to compute. Once we compute 7, why are we computing it again here and again here and again here, right? Okay. So given any recursive algorithm, we would like to ideally avoid recomputing the same problem again and again, right? Okay. All right. So how do we do it? We save it. Okay, good. How do we do it? We save it. How do we save it? Another array. Okay. So here is now here we kind of come to a thing of how do we save problems that we've already computed so that we avoid recomputing it. Okay. There are two ways of doing it. One is that we actually understand the structure of the problem, right? So in this case, what is the structure of the problem? Can we, a priori, we could have decided that there are only n possible problems that I ever need, right? Yeah? Fibonacci has the feature that to compute Fibonacci of a number n, I only need what? Fibonacci of n minus 1, n minus 2, n minus 3 up to 1. So I already know it because it is so simple, right, in the Fibonacci case, right? All the things I need are obviously of size n, and I can use an array to store it, right? Great. But what if I have a complicated recursion? What should I do? I don't understand the problem. Like the independent set, I have a graph and I'm creating 2 graphs. Maybe I'm creating the same graph again and again, right? How do I know? What should I do? I don't know, right? In general, if you have any recursion, you can automatically memoize it. So what does memoization mean? Memoization is the idea that you don't recompute the same thing again and again, okay? But now we need some data structure to help us store these intermediate values, right? So that when we see the same problem again, we say, aha, no, it's the same problem, why am I recomputing, right? So for that, the idea would be, is simply to say, high level, we say, whenever we do a recursion, we say, did we compute this already? If you did, let's take the value. If you did not, let's do the recursion. Yeah. So any recursion can be automatically memoized. How do you keep track of the previously computed values? So this is the key question. How do you keep track of the previously computed values? You have to store it. How do you store it, right? Okay. So you can store it either explicitly, because I know that the array is of only the fixed size, or I'll just use a dynamic data structure. Okay. What does the data structure store? It just dumps my problem and the value to it, right? Whenever I look for a new problem, it'll say, is it in the dictionary? Have I already computed it? If it is in the dictionary, what do I know? Oh, I already computed it, so I'll just take the value. If it is not in the dictionary, I just recompute it, or I need to compute it. Okay, okay, and so so if you don't know the size of the problem that you need, how big of a memory you need, you use a dynamic data structure. Okay, all your programming languages more or less do this. Okay, behind your back, right? Many programming languages will do automatic memoization, right? Especially functional programming languages are going to do automatic memoization. Okay, okay. What dynamic data structure will they use? Okay, okay. So thing is, because what does it mean to do dynamic data structure, right? Because the sub problems here are it could be like some strings, right? Okay, so because the structure of the problems can be very complicated, they use hashing. Okay, instead of using some simple dynamic data structures, they use hashing because the problem structure could be okay. So there is, this is a bit of a high level. There are 2 ways of memoizing a recursion. Any recursion can be memoized either automatically by dynamic data structures, or if you know the structure of the problem, you explicitly allocate memory yourself and keep track of the memoization yourself. Okay? In the Fibonacci case, why did we use an array of size n? Because I knew upfront that the only things I need are Fibonacci of 0 to n minus 1. So it is enough to calculate an array of size to allocate a priori that I should only allocate an array of size n. But that's only because I knew the structure of the problem. Okay, okay. So that is what is memoization. So I'll leave you with the following code, right? I wanted to. Here is the thing. So let's implement Fibonacci, even this efficient algorithm, and see what happens. So I didn't want to write code in the. Here is. I hope it is working. Okay. Do you see this code? This is code chef, right? This is just okay. You can't see this, right? Okay, so this is just the Fibonacci algorithm, the iterative algorithm. So, okay, this is C, my old style C programming, right? And this is even better than the Fibonacci of I am not even allocating an array. Do I need to allocate an array? In fact, you don't even need to allocate an array, because here is the trick. You don't even need to allocate array, because all I need to remember is the last 2 numbers, no? To compute the next number. Okay? So you see this code? This code is what I implemented. Okay? To compute Fibonacci of n, I only need what? Fibonacci of n minus 1 and n minus 2, right? Okay, so I'm building up to n. I just need to store the last 2 Fibonacci numbers. Then I get the next Fibonacci number, right? Then I can get rid of the one before. So then I can go to the next 2, right? Yeah. So to calculate Fibonacci of n, I just need to keep track of n minus 1 and n minus 2. And once I calculate Fibonacci of n, I can get rid of the n minus 2 guy and shift over. So only two is even better, right? You don't even have to allocate memory. That's called spacing. So that's what I implemented, right? You don't have to see the code, right? It's believe me, it's a very simple thing, right? Okay, I just want to run it, right? So I ran Fibonacci of 45, right? So what do you get? This is what it gave me, right? Let's do Fibonacci of 50. It's very fast. I mean, this is a slow. I'm not doing input and stuff, so I'm going to do 50. I hope it runs. It's queued. Okay. Okay. Maybe the network is not working. Okay. Status, internal error. Okay, so what happened, you think? Let me run it again, see what happens, right? I don't know, I just before I came here, I pulled up something online, right? Okay, so it is, I don't know what is causing this thing, but let's run it for 40 and see if it is the code or right. Okay, so what should happen if you submit for 40? Sorry? No, it doesn't mess up. Sorry? Okay, all right, sorry, it's not working. But you run it and see what will happen. It'll give you a negative number. So you say, what's going on? It'll give you a negative number. For 50, it'll give you a negative number. So what's going on? Overflow, right? So you say, wow, 50 itself is overflowing. Why? Yeah, and the number is growing how fast? Exponentially in n, right? Okay, we are just doing how many additions? 50 additions, no? In 50 additions, if you're not careful, you can blow up. Okay? Alright? So you have to be careful. Even though addition is constant time, if the numbers are growing so fast, right, then you'll get bizarre answers like that. Okay? So this is just to tell you that, when you take an algorithms class, you have to be a little bit more careful, right, of the model of computation. Very simple things can blow up on us. Okay? 50 is already overflowing, right? Okay, so the complexity of Fibonacci number calculation is not obvious, right? Okay, in fact, what is the running time of Fibonacci number, right? If I give you n, how long is it taking? Is it exponential time? Yeah, so this is a reasonable thing. How many additions did I do? N additions, okay? Okay, but what is the size of the output? The size of the output is exponential in n, no? So to even write down the output, I need exponential number of digits. Okay? So in fact, to specify n, I need log n bits, right? To specify the output, I need n bits. Okay? So the output itself is exponential in the input, so you can't even have a polynomial time algorithm for this. Okay? So number problems, you always have to be a little careful, right? But anyway, that's not the point of Fibonacci numbers. The two things that we need to remember are recursion and memoization. Okay? And we'll see that there are some recursions. If you memoize, you will get an efficient algorithm because the number of different problems is polynomial. And seeing that and memoizing it is really what dynamic programming is about. How can you develop the recursion so that when you memoize it, you get a polynomial time algorithm or some more efficient algorithm, right? So we'll see how to do it formally in next class. This was a bummer.